I'd like to introduce our next speaker, Mohammad Rezaee. He is the Associate Professor of Energy and Mineral Engineering with the Pennsylvania State University for 8 years. So with that, I'd like to welcome Mohammad.
Thank you. Thank you, Christy, for the introduction, and good afternoon, everyone. It's great to be here today and present our ongoing work on the critical mineral recovery from acid mine drainage, a path that can extend it and enhance the supply chain resilience within the United States. So you've been exposed to a few presentations yesterday and today, and they spoke about the critical minerals. I'll just quickly go through them. 2020, this is the list of the 2022 critical minerals. And as you can see, 50 elements have been listed as the critical minerals due to supply chain risks and also their importance in advanced technologies. However, in 2025 US draft list of the critical minerals, it has been proposed that copper, lead, potash, rhenium, and silicon and silver will be added to this one, and removing the arsenic and tellurium, making it total 54 elements. And these critical minerals have a lot of applications in several supply chain, including the critical minerals and materials, lithium-ion battery supply chain, semiconductor supply chain, and among the several others. And among the critical minerals, so there are 17 rare earth elements, which are 15 lanthanides and yttrium and scandium. And United States has very limited sources of the rare earth elements and is heavily reliant on the foreign sources of these elements. And even the sources that we have, including those in Mountain Pass in California, they are mostly light rare earth elements and not heavy rare earth elements. So it is very important to extract and explore all the secondary sources for these elements within the United States to address the US needs for these elements. And Penn State has been as a long history on the extraction of this mineral from primary and secondary sources, as you can see over here. But at 1952, one of our former deans of the college, Dr. Steidel, mentioned that by the year 2000, we will not be wasting our coal ash, in which geochemists have shown there is a notable concentration of rare elements such as germanium and rare earths. We will be recovering these elements, and that's what we've been continuing on those story. Among the secondary sources, there are a lot of secondary sources for the critical minerals, including the coal waste and coal utilization waste streams, including the coarse refuse, pile fine refuse, acid mine drainage, fly ash, and bottom ash, and also the waste streams of the minerals, other minerals such as the copper, iron, phosphate, bauxite, red mud, along with the recycled materials such as electronic waste and solar panels, and also a lot of wastewater stream in addition to acid mine drainage, oil and gas produced water, and geothermal brines in Salton Sea, California, that they use it for the power generation. And those ones that are involved are some of the secondary sources that we are actively working for the critical mineral recovery at Penn State. So today I'm going to focus on our work on the acid mine drainage. So you're already familiar with the acid mine drainage. Pyrite is the source of the acid mine drainage, and when it's concentrated in the coal waste streams and also the waste streams of the sulfide minerals. And when it's pyrite is exposed with the air and water, is oxidized and generate ferrous iron, sulfate ions, and hydrogen protons. And that is and generate the acidic environment. As the ferrous iron form, it will be further oxidized to the ferric iron, and once the ferric iron is formed, so it can again act as the oxidizer for the pyrite oxidation. And even without independent of the oxygen, pyrite oxidation will further move on and then again generate ferrous again converted to ferric, and this cycle will continue and generate high amount of the hydrogen protons and acidic environments. And in this acidic environment, majority of the major and trace elements, depending of the host rocks and what they are available in the host rocks, they can be dissolved in this acidic effluent, and therefore they increase the high total dissolved solid content and electrical conductivity, and they need to be treated before being disposed to the environment. Acid mine drainage has been of environmental concern for decades, and nationally, globally, and also in our state of Pennsylvania. So as you can see by the UN, it has been reported that by 2030, we will have more than 1.5 billion cubic meters of the acid mine drainage that need to be treated around the globe. In the United States, we have more than 180,000 acres of the freshwater reservoir that are affected by acid mine drainage. And in Pennsylvania, we have more than 5,500 miles of the water stream has been again contaminated with the acid mine drainage that need to be treated again for the environmental compliance. And that treatment requires significant amount of the cost, and therefore there has been some research and that for the how we can make the treatment process more sustainable. So research, recent research has shown, including those one that papers by Dr. Crovato that have analyzed like hundreds of the acid mine drainage in Appalachian, so and along with the publications with the other colleagues, so have shown that there is a significant opportunity in the acid mine drainage, and acid mine drainage can selectively dissolve the heavy and high value rare earth elements in the mine drainage. And also another research has shown that 700 to 3,400 tons of the rare earth elements can be recovered from the acid mine drainage annually. So if we can selectively recover these critical minerals while we are treating acid mine drainage for the environmental compliance, we can increase the sustainability of the process. And that's what I present our ongoing work today. And this can change the AMD from the challenges to opportunities. So from their presentation, so you know already, like there are different type of the treatment, passive and active. This is the typical active treatment in Pennsylvania, and like some of the operations by PA that acid mine drainage are collected in the ponds, and then the pH will be adjusted using the caustic materials, and then when it neutralized, most of the elements that were dissolved in the acid mine drainage, so they precipitated out as the solid, and those solid materials called a sludge, and then as they are accumulated in the sludge in those settling ponds, they will be discharged to the sludge pond, and then they will be dried up in the natural environment. And the water that is now neutral, circum-neutral pH, and as meet the regulations, can be discharged to the environment. Both of these sludge materials and acid mine drainage materials, acid mine drainage streams have been found to have a considerable amount of the critical minerals. And however, if you are going to extract those elements from the sludge materials, it's going to be challenging because we need to again dissolve it and then bring it back to the solution. We separate those materials, which is a soup of the material, and it's very difficult to separate them and challenging. And also, it's gonna require significant amount of the acids for the bringing it back to the solutions. However, if we can separate them while they are in the water streams and acid mine drainage streams selectively, that would be of significant benefit. We have analyzed a lot of sites, including those ones that are operated by PADEP Mission Office and in the Clearfield County. And as you can see, these both AMD and sludge streams of those sites have considerable rare earth elements, about 0.5 ppm of the rare earth elements, or 1,000 ppm in the sludge. And as I mentioned earlier, so acid mine drainage can selectively dissolve the higher value heavy rare earth elements, as you can see from the higher ratio of the heavy to light ratio for these streams. And it is because of this also these streams have been originated from the lower cationic coal seams that also known for the elevated content of the rare earth elements. So these are the acid mine drainage sites. The site one, as you can see again, the AMDs are collected in the treatment ponds and then go to the settling ponds, and then on the side of it is the sludge pond. Same thing for the second site that we have again treatment pond and settling pond and sludge ponds. The third pond similarly, so again treatment and settling ponds and sludge ponds over here. And these sites again, we have a lot of them close by to each other in Pennsylvania, including the Clearfield County that we got the samples from. So in order to modify this AMD treatment process for, as we are treating for the water, for the environmental compliance, at the same time selectively recover these critical minerals, we have started working on how rare earth elements behave during the treatment process. And we took a look at the detailed precipitation behavior of the critical minerals, including the rare earth elements. And for this study, we took a look at it. Typical ligands such as hydroxide, carbonate, phosphate, ammonia, or sulfate that could be potentially used for the rare earth elements precipitation and through the stage precipitation process. We use the sodium hydroxide as the baseline, as you can see on the right-hand side graph. And the red line is the recovery, total recovery, as we incrementally increase the pH. So you can see we can reach to the high recovery of the rare earth elements at elevated pH around 9. So using the hydroxide treatment, we would need record elevated pH. And even at that elevated pH, we would need, like, we still lose about 15 to 20% of those REEs in the effluent. And another thing is, if we cannot discharge a very high pH material, and again needs to be come back to the circumneutral pHs. And on the on the left-hand side, so then among all the other ligands that we have studied, so you can see the carbonate and phosphate treatment for the rare earth elements precipitation brought the precipitation pH, maximum precipitation pH of the rare earth elements to below circumneutral or below pH 7. And we can reach about 95% recovery of the REEs through these two ligands at the below pH 7, that is target pH for the AMD treatment. And among these two, we focus more on the carbonate precipitation using the soda ash and to provide carbonate ligands. And as you can see, again, we can reach to the maximum RE recovery at about 95% at pH around 7. And the reason for that, the precipitation pH below pH 7 is that carbonate formation products have a lower solubility and gives free energy compared to the rare earth hydroxide products. And again, another reason for the selecting carbonate was that it provided us a selective separation window for the separation of the rare earth elements and aluminum. So if we take a look at the other elements behavior through the carbonate precipitation, we found that, look, so RE is we can separate the aluminum at the pH around 5 without losing, with a minimal loss of the rare earth elements. So, but at the same, phosphate didn't provide us this selectivity, so we move forward with the carbonate precipitation to take advantages of bringing the maximum recovery to below pH 7 and also selective recovery of and separation of the aluminum and rare earth elements. Which is very, the separation of the aluminum and rare earth elements is very important because both of them are trivalence elements and their separation in downstream processes would be challenging. So if we can, again, maximize their selectivity during the treatment process would be significant beneficial, and then reducing the cost for the downstream purification processes. So we turned out the treatment process till this point to a two-stage carbonate precipitation process that we, through the carbonate treatment, we go to the pH 5 and recover our aluminum, about more than 90% of our aluminum, and then we will go through the second pond or second tank for the treatment to go to the pH 7, and then we recover our rare earth elements. So these two-stage carbonate precipitation result, as you can see over here, were confirmed in the combining the pH up to pH 7, followed by then and recover our aluminum, and then going to the pH 7 for recovery of our rare earth elements. In the first stage, we recovered more than 90% of aluminum with minimal loss of the rare earth elements in this first stage, and then in the second stage, we recovered we obtained high recovery of the rare earth elements with minimal contamination of the aluminum. And the results have been published in multiple articles, including this one, effect of various ligands on selective precipitation of the rare earth elements, and I'm happy to share our articles with you if you are interested. Also, for providing CO2, for providing carbonate ligands, we tested the CO2 mineralization process that during the treatment, if we can use the CO2 sequestration to to provide also CO2 carbonate ligands, and the results were similar to the soda ash. And we could, through this process, also we could obtain the two-stage separation process for the aluminum and rare earth element separation at two-stage carbonate precipitation process. And we found that the carbonate precipitation followed the enthalpy of hydration of the rare earth elements through the carbonate precipitation process. Again, this one has been published in the for the CO2 mineralization process. It's been published in Chemical Engineering Journal. Happy to share it with you. So here is so far was our two-stage carbonate precipitation process that we selectively recover aluminum and REE. We modified it further for the iron separation as well to turn in it to minimize the carryover of the iron in the aluminum and rare earth elements as well. So for the pre-treatment process, we can use the aeration process, to oxidize the iron and precipitate it at pH around 4. And this way also, again, we get the higher quality of the aluminum and RE product. And for the aeration, we can use like technologies available out there, such as Maelstrom by the Somerset International, that they also for in our pilot scale effort, they provided their unit for our pre-treatment. We further conducted the kinetic studies of the precipitation and then consider different stages of the precipitation, including the nucleation, growth, ripening, and aggregation, by monitoring the concentration over time and then particle size over time. And this was conducted in order to understand the process mechanism, and at the same time the precipitation rate of these materials, that the mechanism was driven by the supersaturation of the elements, and then the rate depends on how high is the supersaturation of these elements are. And we utilize those precipitation rate for the understanding like how long time we would need for the retention time in our ponds or in tanks for the scaling up our process. And we utilize them for the process scale up, and they have been also published in the RCR journals. So now we have obtained in our process, we have obtained the iron, aluminum, and REE through the process. So we wanted to further increase the purity of these products. For the purification of the aluminum, so we use the process of the aluminum products, because what we got through the process in the precipitate was about 30% purity of the aluminum. So then we utilize the process that is being used in the bauxite mining. And then so we go through the dissolution of the precipitates in that stage with using the sodium hydroxide at pH around 12, and then we purge CO2 to bring for the selective dissolution of the aluminum over here, and leaving the iron and other contaminants in the solid, and then the solution goes to the CO2 mineralization that brings the pH to around 9, where the aluminum is precipitated, and we get more than 90% aluminum purity from this process. The REE cake or precipitate purity that we got in this process, it was about 2% from the from ppb level in the acid mine drainage, so we could concentrate them about a couple of percentages in the precipitates. So then in order to again upgrade that one and concentrate that one, instead of the costly processes such as solvent extraction on or oxalate precipitation, we took a look at it, what was the impurity in that one, and the impurity of that one was like mostly iron and aluminum. That again, if your 90% of that one is recovering in the first stage, that left remaining 10% of the high amount of the aluminum acid mine drainage is much more than the amount of the REs that were initially existed in the acid mine drainage. So even that 10% of the aluminum could bring the grade of the RE down. So then based on this, we, rather than costly processes, we repeated our process. So we dissolved it in the acidic pH, and then we went through the repeated this process, pH 5 again for the 90% of that 10% of the aluminum was carried over is removed. Again, we get a higher purity of the rare earth elements, and again we repeat this process, and we get about 90% rare earth purity, mixed rare earth elements. So again, here we fully characterized our product, and as you can see, we could obtain 90% purity of the aluminum, and then rare earth elements purity about 88% in terms of in form of the carbonate, which could be also calcined, and then obtain more than 90% purity of the mixed RE oxide. And then I'll talk further about the transition metals, including cobalt, nickel, and manganese further in the next slides. So again, our purification process has been also published, and all the details are available to public. So now we are at pH 7, and we treated water, but still there are other critical minerals, including transition metals such as cobalt, nickel, manganese, zinc, and there are significant like reduction of the manganese regulation, like manganese level for the in terms of the regulation for the AMD treatment. And typical treatments for the manganese and other transition metals, cobalt, nickel, zinc, so are that they can be, here is the per bay diagram. So basically it shows at what pH and EH these elements can precipitate. So we can go horizontally and elevate the pH around 9.5, 10 to precipitate the manganese, cobalt, nickel, and transition metals. And that's the one process that is being also practiced in active treatment. So some of the sites that, for example, we visited, they go to the very high pH around 10, and then they add citric to precipitate the manganese, and they added again citric acid to bring the precipitation around the pH 7, so they could discharge it. Or we could go, or we could go vertically and oxidize these elements and precipitate them through the oxidation precipitation, such as in form of manganese oxide. That again, some of the practices such as potassium permanganate treatment for the low flow rate acid mine drainage system. So we took a look at these various process paths, and then in order to address the challenges, including the again they need either for the precipitation a high pH value or costly oxidant. So we took a look at it again, the effect of the various ligand and oxidants in precipitation of those transition metals. And we found that among the various ligands, ammonia provided the highest recovery, but required the elevated pH around pH 9.5, 10. And then among the various oxidants, ozone provided us with the highest recovery among all oxidants and ligands for the precipitation of the cobalt, nickel, manganese, and we could also obtain close to the mineral sources of the purity of for those minerals. And so we selected ozone for the oxidative precipitation process of these transition metals, which has a very high oxidative potential compared to the other oxidants, and also at the same time it's a chemical less process and more environmentally friendly. It can be generated on site through the ozone generation units, because the ozone treatment is being used for the municipal waste stream treatment for deodorization of the municipal waste and other larger scale application, but their application for critical mineral recovery was not explored, so we took a look at that one. And it does not introduce impurity into the final product. And then for the implication of that one, it requires further TA techno-economic assessment. Again, we have published our ozone oxidative precipitation process of the critical minerals in a few articles. Recently, we have also worked on our precipitate of this process, which is again contain cobalt, nickel, manganese, zinc mix. So we developed our purification process combining ozone oxidative precipitation, sulfide precipitation, DMG for the nickel, and then again for the also cobalt and manganese using the combination of the ozone, DMG, and sulfide precipitation, and we were able to obtain close to the 90% or over 90% purity of these individual elements, cobalt, nickel, manganese, and zinc, from the final stage precipitates. So at the end, we combine these two patented processes, the carbonate precipitation and ozone oxidative precipitation process, to obtain a flow sheet. So again, as a recap, so we are going first through the pre-treatment to recover our iron. Then we will go through the pH 5 through the carbonate precipitation to recover our aluminum, and then pH 7 in the third point for our first tank or reaction tanks to recover our rare earth elements. And then after we recovered our rare earth elements at that pH 7, we purge the ozone, and then we recover transition metals in the acid mine drainage. And then we will go through our purification process to obtain close to 90% purity of those elements. So based on the scale-up parameters that we obtained in our study, so we started first as a lab scale, then we validated the scale-up parameters through the bench scale continuous process. Then based on when they were validated, so then we designed a 10,000 gallon per day treatment process, and then we built it at Penn State, and now we are operating it. So here is our facility. So you can see on the so we have a large tank, 4,000 gallon tank that we fill it up with the water tanks that we bring it from the site. So then those water is coming from the outside of the building. It at the 7 gallon per minute. It will be fed with the gravity to the first unit, which is our iron precipitation tank. Inside of that one, we incorporated the maelstrom technology for the iron oxidation, and then we adjusting the pH by the sodium carbonate, and then when the iron precipitation is formed, so it goes through the settling tank. Through the settling tank, they are precipitated, and then we will have our water flow goes through the filtration process to recover our iron, and then goes to this buffer tank and will pump up to the next stage. Again, the adjustment of the pH to pH 7, precipitate aluminum settling tank, and then filter our aluminum product, goes to the next stage for the rare earth elements recovery at pH 7, then settling tank of the rare earth elements and filtration of those one, then goes to the after REOs are recovered, so it goes through our ozone oxidative precipitation process that we purge the ozone, and then it goes through those transition metal are oxidized and precipitated out from the solution, and then go to the settling tank and filter, and the water can now meets the requirement for the treatment, and then is discharged. So here is our products of the iron, aluminum, rare earth elements cake, and cobalt, nickel, manganese, zinc cake that we get it from these 4 stages that you see it over here, and these are the associated products on the other side of this building. So we also have so here is our plant when it's operating. So we have a lot of our graduate and undergraduate students involved in this project. And on the other side of that building, so if you stay on the other side, so you see our also purification circuitry which is much smaller because we just purify the collected cake materials from each stage. And then again, as I mentioned, for example, you see REE, we will go through this solution and then repeating of our carbonate precipitation process to get the 90% purity of our rare earth elements, and also along with the other metals that we obtain. We all recently have also formed the alliance with the major industries within the US to convert these waste streams to high-tech applications and increase the completely domestic supply chains of the critical minerals. As you can see over here, we are from the Pennsylvania waste streams, such as the acid mine drainage and coal clay sources. We extract these critical minerals, and then once we extract them and purify it to the 90% purity, they go to the mixed rare earth products go to our partner rare earth salt company, and again, it's a US-based company that they separate those rare earth elements to individual 99.49 or 59 purity of the individual rare earth elements, and our cobaltic and manganese that we got at about 90% purity, it goes to the other industry partners, Aqua Metals, and they conduct the uh, separation of those one, like purifying to 4.9 or 5.9 purity. Then our colleague at the University of Virginia, they have developed a low temperature metallothermic reduction, so to turn the oxide to the metals. And then the rare earth metals, then along with the cobalts and other critical minerals, go to the GE Aerospace, and then they make master alloys, super alloys, and rare earth magnets, and they tested for the defense applications. And then they also conduct a complete integrated techno-economic and life cycle assessment of the process. So that's a project that we are working on that one, and it's continue for the next 3 years. And with that, I'd like to acknowledge Pennsylvania Department of the Environmental Protection for providing us access to the sites for the samples and feedstock for our processing facilities, and also providing access data through the Meshanan District Office. U.S. Department of the Energy for their support through the LTI and NETL, and Somerset International for loaning us their milestone for oxidation for the iron stage precipitation and pretreatment, and Penn State Center for Critical Minerals. With that, I thank you for your attention. It was a pleasure to be here today, and I'm happy to answer questions that you may have.
Does anyone have any questions for Mohammad?
Have you done any economic analysis of that process to see if the materials you're producing are exceed the cost of producing them, or have you not done that?
That's a great question, and that was one of our goals of this process. So right now now that we are operating our pilot scale, so we are obtaining all the techno-economic and life cycle assessment data to conduct the detailed techno-economic assessment and life cycle assessment. Maybe next time that I present those data will be available as well. But on the treatment side, we modify the current active treatment processes to multiple stages. So try to minimize the cost by modifying what is available out there already. Yes, please.
Yes, so you had mentioned 3 different AMD sources.
Yeah.
Are you collecting from one in particular, or do you mix them, or how do you deal with that?
So like right now for our pilot scale, one of them is easier to access. So like we will go, and they are again operated by PA Meshanan District Office. So we will go, and then on a daily basis, multiple trucks go back and forth, and then bring the continuously fill up our 4,000 gallon tank, and then we feed it to our process plant. So we characterize that one, and along with the other sites, but for the easy access and closer to campus, so we are using one of them right now. But we are also soon we are going to again further scale it up, rather than 10,000 gallons. So we are going to which is equivalent to 7 gallons per minute. We are going to scale it up to the larger scale. For that one, we are looking for the new site opportunities as well.
Any other questions?
Thank you so much.
Well, thank you, Mohammad. Right now we're on a short break between the presentation. 10:45. And just as a reminder, if you guys could fill out your evaluation surveys, they help us plan for next year's event. Thank you.
Thank you. Hello, Chuck.
I'm Chuck.
Nice to meet you.
Shine. I have some ideas that might be able to help you.
Sure. Thank you.